Welcome to the Cosmic Pie Podcast, episode 3, year number
4. Quattro.
4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live on the campus of the University of North Dakota. Unless you're watching us like 3 days from now.
Right. Then
Hopefully
we're not live.
Hopefully we're still alive,
Right.
but we're not live.
But we're not live.
So
I don't know. 4 days from now, it's supposed to get pretty North Dakota.
see if we can survive this,
Right.
hopefully the worst part of the winter.
Right.
Come out on the other side and pray for spring. Is that the idea?
That's the idea.
Anyways, if you have any comments or questions that you'd like to ask us during the podcast, feel free to send them in and we'll stop what we're doing and take a peek. And if we enjoy your comment or question, we'll mention.
Yeah.
We could even answer some questions.
We will hopefully even answer it.
Yeah. Now, Robert,
Yes.
what do you think it's time for?
Let's see. What haven't we done yet? Oh, the disclaimer.
The disclaimer.
Yeah. So the disclaimer is the opinions and beliefs and all the views expressed herein are those of myself and Wayne, and not those of the University of North Dakota or the Department of Physics and Astrophysics, College of Arts and Sciences. It's just us. We're here talking at you.
That's it. And by the way, if you prefer not to watch us on YouTube, we do upload our recordings to Spotify the next day.
Mm-hmm.
So you can always check us out on there. And don't forget that if you like what you hear, please give us a thumbs up. That lets us know that we know that you like the podcast, and that keeps our motivation for doing more.
For doing more instead of it waning and
Getting smaller and smaller, and then we just give up at some point, right?
right. Well, I don't know. I'm pretty stubborn.
When the viewership gets only one person watched it in a week,
Well, that would be discouraging.
that wouldn't be too good. But anyways, and there's so much going on in space, that would be a crime.
It would.
Because people will miss a lot of what's going on out there if they don't have time to dig into this information themselves.
There's a lot going on. There's a lot of reasons to look up.
We're here to help you.
That's it.
There you go. Now, to update people, if you want to start with the first item here,
Sounds good.
we talked about the fact that NASA was going to perform its first ever medical evacuation the day after our last podcast, last Tuesday. And that did indeed occur. So that was Wednesday evening, our time, that the Dragon capsule separated from the International Space Station, bringing the crew, Expedition 11, the crew of 4 home early. Now, we don't know, of course, which astronaut had an issue, a medical issue, and we don't know how severe it is. I mean, obviously that information is private, as it should be. If they want to let us know in the future, the individual that it affected, I'm sure they would do that.
Right.
Sometimes they put it in a book, and we know like 20 years later what happened, but so be it. But at least the return was uneventful, which is a good thing in space exploration.
Absolutely.
And if they need any help, I'm sure then they're receiving the proper medical care. So that's a good thing.
Yeah.
Now,
With human space adventures, they should never be treated as becoming routine, but they should become routine.
well, you could kind of think of it like an airline.
Right.
Right. I mean, is it routine to call the flying of a plane with 200 people on board, many thousands of times a day worldwide? Yeah. Is that routine?
Absolutely.
And how long have we been doing that? How many decades?
Right.
Now, is it routine when an individual gets in a plane maybe once every couple of years and is a little bit scared, for lack of a better word,
All right.
Of course. And that's normal. So it's not routine in that sense, but...
Right. And that's kind of what I'm getting at. I mean, the people involved should not be getting lax because, this is just another routine descent. They should be treating it as something could go wrong at any minute. But hopefully it gets to where things just don't go wrong.
Yeah, and you just brought up an idea that I had too, is later on this month is when we commemorate the loss of the Challenger.
Right.
And then on February the 1st is the Columbia.
Yep.
And so those two events, because they've happened, within a few days, different years, but within a few days of each other, that NASA has a memorial for them at the same time.
Right.
And even the Apollo 1 fire happened in January.
Oh, I didn't know that.
So in some sense, 3 of them happened in relatively close approximation in terms of the time of the year.
Yeah.
So we can say something more about this maybe next podcast.
Yeah, that would,
and why I think about it is because you mentioned that it's space flight, space exploration. It's never really routine. Well, there's examples right there.
Right.
And if you get off your game, you get distracted, bad things can happen. And even for airplanes, right? How many airplane accidents have them because of human failure to either, report some problem higher up, so it gets propagated through the whole maintenance sort of routine and program,
Right.
or whatever. Things happen,
There you go.
and unfortunately, that's the way
Unfortunately.
we can only try to do better and better each time we learn from whatever happened prior failure to make sure it doesn't happen again going forward. But
That's what you do.
now, speaking about going forward, the big event that happened past weekend, of course, was the rollout of the Artemis 2 rocket, the Space Launch System, SLS, to the launch pad at the Kennedy Space Center. So I actually was up all night working on research and therefore was wide awake when they started rolling out the rocket early in the morning. You might have noticed I made a post of.
I did.
Yeah. So, and it takes a long time. It's like on the order of 12 hours to go from the vehicle assembly building where they stack the vehicles. And it's the same building, by the way. It was initially built for the Saturn V, for the Apollo program.
Right.
And it's large enough that you could put 4 Saturn Vs inside of the building at one time.
Oh, wow.
They had divided sort of in quarters, and each quarter can handle a Saturn V.
Wow.
And same, of course, it was modified for the space shuttle, and you could do the same thing. You could fit the space shuttle, of course, in that. And it's the same ideal here with the SLS. The rocket is even taller, a bit taller than the Saturn V. So it's you don't have to build a new building for it, which saves a lot of money. You just can reconfigure the old vehicle assembly building and use that.
Right.
And if things get going, you never know, right? What happens here? Maybe
they'll be stacking 4 at a time.
Maybe they will be stacking 4 at a time. In fact, the astronauts who are going up on the Artemis 2 mission and the current NASA administrator spoke to the media on Saturday morning about the flight. And they mentioned, looking forward to Artemis 100. So that's interesting, whether that's going to the moon or heading to Mars.
Right.
But obviously you want to be optimistic in the program. I mean, you're putting your life on the line to do this sort of stuff. So
You really are.
you really are. You're setting it out there. But it was nice to see the vehicle. It's just one of those benchmarks that you make on your way to going back to the moon. And so the idea, which you can see the windows of launch opportunity at the bottom of the image. The first one starts in February. Whether to make the February one, who knows? So there's like 6th to the 8th and 10th and 11th. If they make it, they make it. If they don't, they don't. And there's a lot of work that needs to be done to the rocket to prepare it for launch, of course.
Right.
And you want to be able to go when things are right. If you still have, if you're rushing to get things done, maybe you want to just hold off and try to make the March launch opportunity. Mm-hmm. And there's no reason why you have to rush it in March and not wait till rush it in February and wait till March or even wait till April. There's nothing that we have to get up that. How many years have we waited since the last time we've been to the moon in 1972, right? It's 50 years or whatever it is.
Something like that.
Yeah, 50-some years. Yeah, it's... I know. Back in the early 70s, if you would ask the average space enthusiast on the street, where do you think we'll be in 2026 in terms of human exploration of space?
We'll be in the moons of Jupiter.
Yeah, we'd have bases on the moon, and we'd be already on Mars in the 1980s, and we'll be on the moons of Jupiter and Saturn, and we'd have nuclear rockets flying around, so it only takes a few months to get out to Saturn rather than years and years, and, be all this kind of stuff. But, what that's one of the things that's hard to predict is the future, as Yogi Berra said, right?
That's it.
Anyways, so you never know what happens. So hopefully they make the February deadline, so if you get a chance to get down in February to the Kennedy Space Center, that would be a great sight to see. Mm-hmm. As far as I know, it's going to be launched in the evening. And so that would be a fantastic. The first one, Artemis 1, which was unmanned, that was also launched in the evening. And so that was just a nice sight to see, the tremendous power of the rocket. Like I said, this is the largest rocket that NASA ever built or had put together.
Right.
So it's going to be really neat to see this go up. Anyways, we'll see how it goes. So hopefully the flight will be a good one. And speaking about the flight, if you never paid attention to what the Artemis project is all about and what's going to happen on this flight, here's kind of an artist drawing to give you an idea of the main points here. So the idea, of course, is first to get launched from Kennedy Space Center, go in orbit around the Earth, and that's the place where you want to check out all the equipment.
Right.
You don't want to wait until you're halfway to the moon to check things out. It's like, maybe we shouldn't have went to the moon, right? We should have just stayed in low Earth orbit and then came back. So you check everything out, make sure it's all okay, and then you do this sort of translunar ejection burn to send the spacecraft towards the moon. And it's called a free return trajectory. You might have heard that language used if you watch like the Apollo 13 movie.
Right.
Or if you watch the documentaries on YouTube or something like that, that shows you what was said during the time. I think, what was that, 1970, 71 when Apollo 13
Somewhere
happened?
around in there, yeah.
Yeah, Apollo 13 happened. They use this free return terminology, and what it means is you just burn the engine to get out of Earth orbit heading towards the moon. And of course, you aim ahead of the moon, so by the time you get to the distance that the moon is from the Earth, the moon is there. But not right there, but just off the side. And you swing around the backside of the moon, the far side of the moon. So you don't need any gravity, like you don't need any extra engine power to take you there. You just naturally go around the moon. There's, of course, corrections that you can do along the way.
Right.
And then you swing around the moon, but you have enough speed that you actually can escape the moon's gravity and swing out the other side, as you see there in the diagram, and then make your way back to Earth for landing.
This gets into why I describe to students a lot of times, especially intro-type students, that being in orbit is falling towards the ground and missing because you're moving to the side fast enough that you miss.
Yeah, we always say if you think of a satellite, for example, in orbit around the Earth, you can envision it as falling around the Earth at a certain rate, if you like, that the Earth curves away from it at the same time.
Right.
So you never hit the Earth's surface in that sense. So you're continually falling around the Earth, and that's why you're weightless on a spacecraft, on a satellite like the International Space Station, is you're falling around the Earth.
Right.
But the path is such that it doesn't hit the Earth, so you're just continually falling around.
And that's why the term has come to be microgravity instead of weightless.
In fact, saying zero gravity in space, which we've used since the space age began, was really a bad
idea.
Bad idea, because that really puts a lot of confusion. Because a lot of people, when they're first learning this, young students think that there's no gravity in space, and then you say, well, then how does the moon maintain its orbit around the Earth? How does the Earth maintain its orbit around the sun? How does the sun maintain its orbit around the center of the Milky Way, and etc.? So clearly there is gravity in space. So that was a bad use of the English language at the time.
Yes, it was.
So anyways, the thing you might wonder, though, is what's going to happen after Artemis 2. So let's say everything works okay. Artemis 3 is the really inspirational one to wait for, and this is actually landing humans back on the surface of the moon. Now, one of the things you might wonder, why do this free return? Just go around the moon, come right back. In fact, we're not even staying in orbit around the moon. We're just looping around the backside and heading right back to Earth again. Why aren't we at least trying to land on the moon? Well, we have no lander, no vehicle that'll take us from lunar orbit down to the surface of the moon and then back up to lunar orbit again.
Weren't we supposed to have that by now?
We were. I mean, we need something to do the job of the lunar module, if you remember from the Apollo project.
Right.
But back in the Apollo days, even the lunar module was way behind schedule.
Yes.
And we're running into the same kind of issue here in terms of scheduling, not for different reasons. Now, you can see two ideas that are presented in this artist's drawings. The one on the left is the one from SpaceX. So NASA issued a contract to SpaceX to use their Starship, which we see lots of launches happening from Texas, and they're improving their technology all of the time. So the goal was that SpaceX would mature the technology so it could use the same type of vehicle to land on the surface of the moon and then back up again. But I remember looking at like drawings done way before the Apollo program. Like books that you can read. This is what we envision that it will look like when humans explore the moon for the first time, right?
Right.
And they have these kind of setups, right? We have these tall, huge rockets landing on the moon. And you wonder, where's the center of mass? It looks so unstable.
Right.
Like it wouldn't take much if you landed on half a crater, right?
Top.
Yeah, it would fall over or something. So you have to be extremely careful. And look in the drawing. You actually have to use sort of a lowering and lifting device to lower down like the rovers because you're so high up above the surface.
And I'm just thinking of the mass that entails that could be put to better use for other instruments and things like that.
You can have
if that's what they're going for, I'm not so sure.
You can have elevators that take you to other parts of the rocket from inside if you're an astronaut. I mean, it's kind of seems, I don't know, lack of better words, way out there in terms of our getting back to the moon, at least by what, 2030? We'd like to get there before then, but by at least 2030.
Yeah.
And this stuff, I don't know if this is going to really work. It can surprise all of us, and it works like
a charm.
Works like a charm,
Yeah.
and it's not an issue, but it looks pretty complicated for that. Now, on the right side, in some sense, it's closer to what we had in the Apollo project. It's sort of a glorified lunar module, and this is built by
Blue Origin.
Blue Origin. So there's two contracts awarded. Now, if they do well on this vehicle, it could work, I think, even before it's Starship.
Yeah.
So in some sense, Blue Origin could have, if they would have had the push and the investment, I guess, could have probably had something ready to go to meet the 2029 time frame and get there before 2030, which was the initial kind of goal to do that. But I don't know. We'll see. A lot of it, like this development work, needs to be done. The stuff needs to be proven. There are other countries like China that plan to go to the moon, and they've already been testing their lunar lander, and they are pushing for the 2030 time frame. So we'll see how this all works. But, I mean, we got to do it safely, obviously. You don't want to rush the technology, and it's not ready to go.
Well, we did that once, and we got away with it.
Yeah, exactly.
We did that once, and we got away with it.
Yeah, I had to be very careful. In fact, hopefully this is sustainable in the sense that we're going back to eventually put a base on the moon, like we have bases in Antarctica, and then to use that as a proving ground to move on to other places, other destinations much further out in deep space.
Right.
And the medical evacuation from ISS kind of proves the point. So if even when you're in the moon, that's going to be several days' journey to get back to the Earth. So you could do that depending, of course, what the issue is. But if you're in Mars, that's a whole different ball game altogether.
You're months.
Yeah, you're months from help. So you need to be able to take the equipment and have the expertise on station with you, people who know what they're doing to operate the equipment in order to maybe perform, like I said, operations. And if you're on a planet or you're on the moon, it's a lot easier to do an operation than if you're in orbit, and weightless environment.
My micro-G issue.
Yeah, the flow of blood and fluids and stuff, that could be a real thing you have to watch out for. Rat's nest in a sense, right? So look out for that kind of thing. So hopefully everything will go good. So the thing to watch out for is in early February to see if NASA makes that open window and launch of the Artemis 2, which should be a fantastic mission, and everything should go well. Listening to the astronauts, it was interesting, and I won't mention the name, but one of the astronauts mentioned, because he said, are you kind of worried about it? Well, you're going on board of a rocket, which has enough fuel and oxygen source to cause a major explosion if it all blew up like a bomb. Of course you'd be worried.
Of course you're worried.
And, well, in fact, you're worried when you go on a normal airplane. A lot of people are worried, right, as we talked about already today. And he said, well, basically, I took my oldest son and showed him where the wheel is and told him about different things that he has to do in case I never come back. And you have to be prepared. And
that's
in fact,
what you do.
And in fact, he mentioned that, in fact, I think everybody should do that because you could go to work someday and never make it home.
Right.
For heaven's forbid, we don't ever want to see that.
Hopefully we don't want to hear about that.
Yeah, but it could happen, right? A tragic car accident, whatever. So people should know what to do in case that.
Yep.
Anyways, so hopefully everything will work out okay, and you don't have to worry about that kind of stuff. The other thing I wanted to note is we've had several months ago talked about the new spacecraft that was launched called SPHEREx. So this is an infrared telescope. It's in orbit around the Earth and does this all-sky survey at the wavelengths of heat.
Right.
And that's how we detect infrared light as human beings. We don't detect with our eyes. Our eyes are not sensitive to infrared light, even though it is light. But we do detect it in the form of heat. And to give you a good example, it's a thought experiment. Don't do this in practice, and don't really do this, is go to your kitchen at night, turn on the element to a stove. Maybe you're going to heat up water for tea or coffee or whatever. And when you're finished, you pour the water in your mug, turn off the element. And when you turn off the element, right away it's red, right? Dark red in color usually. Turn off all the lights in your kitchen if you can. And watch what happens to that element. And as that element cools down, it gets redder and redder and dimmer and dimmer and dimmer. And eventually you no longer can see the element. It's completely dark. And then envision, this is the part I don't want you to do, it's thought experiment only. Take your hand and place it on top of the element. and you're going to get burnt.
Yes.
Now, why
it's still
is
quite
that?
hot.
It's because there is still radiation, light that's emitted from that element, but it's at a wavelength we can't see with our eyes, which is why it looks dark. And a lot of it at that point is in the infrared.
There you go.
So we can detect infrared light as heat. So this telescope then can detect heat. So obviously the telescope itself and its detectors, its cameras, in other words, have to be at a low temperature in order to detect the heat signature. In this case,
That's why such are limited in scope, because they have to carry coolant with them.
So you want to have it at a lower temperature than what you're trying to detect, the astronomical sources that are out there. So the nominal program or mission for SPHEREx was to do 4 all-sky surveys, and then you can stack that data together. Now, we've done this in the past, so you could ask, what's the big deal?
The Spitzer and a few others.
Well, IRAS back in the 80s
IRAS,
did the first all-sky survey. That was a NASA infrared telescope that was launched in Earth orbit as well. But this particular telescope is using very narrow wavelength bands in the infrared. In fact, 102 of them.
Wow, that has got to be pretty narrow.
So
then. Yeah.
typically, like IRAS, we observed in 4 different bands, and that's kind of typical, these telescopes. And that'll give you some useful information about the nature of the object itself to see how bright it is in these different wavelength ranges or frequency ranges. And in this case, these ranges, these bands are very, very narrow. And it's almost like you're actually taking the spectrum of an object.
It's still a discrete spectrum, but it's a spectrum at that point.
So a spectrum would be how bright is the source that you're looking at as it relates to wavelength or frequency. And so you've heard hopefully of absorption lines or emission lines. So if you kind of plot the brightness output from an object as it relates to wavelength, let's say you start at one wavelength value going to increasing wavelength, you'll see this up and down motion essentially of the light output. And it can cross various lines which are related to the composition of the object itself. And that's how we can tell if a star, for example, has, carbon, nitrogen, oxygen, hydrogen, helium, magnesium, calcium, and so on, is by looking at the lines, as we call them, in the spectrum. So you can get a lot. It's like doing the DNA analysis of a star.
Right.
It's kind of like that.
And then there's all kinds of other other information you can get based on how broad those lines are, which direction they're broadened, how they're flattened at the top, and so we can get to the pressure of the photosphere of that star, just all kinds of information from the spectrum.
We can tell if a star is rotating and how fast it's rotating. We can tell if a star, let's say, is approaching us and how fast it's approaching, or maybe it's moving away and how fast it's moving away, whether it has a magnetic field and how strong that magnetic field is. There's a whole host of information that we can get from the spectral analysis of astronomical objects.
Right.
And that's really where we get a lot of our information from. And so using this telescope, SPHEREx, because we have a lot of these bands or sampling, if you like, of the spectrum of objects, we can say a lot more in terms of the nature of these objects than we could in the old days, if you like, when we only had like 4 of these bands.
Right.
And so this is going to give us a vast amount of information of objects. And you might say, why the infrared? Well, number one, a lot of the objects that are at large distances from us, a lot of those interesting spectral lines that normally would appear in the optical are actually redshifted into the infrared. So we can do some detailed analysis then of these very high redshift objects.
Right.
And the other thing is, when we're trying to understand, let's say, star formation, a lot of that's from the heat signature, of interstellar matter like dust or gas. And to understand the infrared light that's emitted from those type of sources tells us a lot more about where stars come from. What are the details of how you form a star? Why do you have different types of stars?
How do you get a cold enough cloud to actually have it collapse and form stars?
All of these sort of things we need to address, and we still have a lot of work to do. So this will really, push us into our advancement of knowledge with this type of mission that we see here.
And
so
I'm just going to look at the picture here. I'm guessing that's an infrared view of the Milky Way.
Yeah, so this is an all-sky projection.
Okay.
That bright band you see running horizontally through the middle are infrared sources in the Milky Way galaxy. And you also see stuff above and below. A lot of that stuff is right around us, like above us, because The sun, along with the rest of the solar system, orbits essentially in the plane of the Milky Way galaxy. So we got to look out through that dust that's emitting infrared light. And you can actually see other galaxies. If you look to the right of center, but down below, there's a little blotch there. It's, I don't know how to describe it. It's halfway between where it says credit NASA and the very center of the image. Halfway there, you see a blob, sort of whitish light.
Mm-hmm. That's the LMC, Large
Yes,
Magellanic
that's the
Cloud.
large and small Magellanic Clouds.
And the small one is that little blob, very little blob to the lower left.
Right, and the Large Magellanic Cloud has a lot of gas and dust.
Right.
And therefore a lot of ongoing star formation.
And since it's bright.
And that's the reason why back in 1987 there was a supernova light that reached us from the exploding of a massive star in the Large Magellanic Cloud. It's a stellar nursery. And a large one. So there's a lot of gas and a lot of dust, and that dust emits infrared light. That's why it's bright to SPHEREx.
Nice.
Very nice indeed. Now, talking about space exploration, of course, the United States, as well as its partners, and there's the Artemis Accord, and then I forget the number of countries that have signed up to it. It's like 60 or something. It's a huge number. Every few months we hear of another country that's signed up to it.
Right.
And this is to provide something to the Artemis project, to sign on, to do things that will help the exploration of the moon and beyond. Well, other countries are involved in things too, besides the United States and its partner countries, and this includes China. And China is using its human exploration of space, in this case, the Chinese space station, to promote or aid the exploration of objects through astronomy with the use of telescopes. And in this case, they are building what's called the Chinese Space Station Survey Telescope.
Interesting.
And the telescope itself is about 2 meters in diameter. And you might say, okay, well, how does that compare to, let's say, the Hubble Space Telescope? The Hubble Space Telescope has a mirror which has a diameter of 2.4 meters. So it's a little bit larger, the Hubble, than the one that's China currently building. But of course, everything is not in the size of the telescope. You could have a smaller telescope, but have a way more sensitive detector or camera, and you can see more things than what the other telescope could see.
Right.
So there's a combination of mirror size as well as the instrumentation that really matter here. So the Chinese space telescope is going to be launched by an unmanned rocket. And one of the things they're planning to do is they're planning to have it serviced by astronauts, ticonauts as they call them, on board their space station. So their space telescope is going to be launched in an orbit that's very similar to the Chinese space station, which means the inclination. Mm-hmm. So it wouldn't take a lot of effort to have this space telescope rendezvous with the space station, and then humans can then make repairs or upgrades to the telescope. Now, NASA has done that. In fact, when the Hubble Space Telescope was first launched several decades ago, they found out that the mirror was very accurately polished to the wrong spec.
Right.
So there was like an instrumentation issue on the ground where they polished the mirror not to the right shape, and they couldn't focus the telescope. So it was a major embarrassment to NASA and the United States at the time. And I'm old enough to remember that. Hubble Trouble was the headlines in all the newspapers at the time. And so NASA, with the engineers, devised a really clever plan to go up to the Hubble Space Telescope with the Space Shuttle, and it was launched from the Space Shuttle. That's why it has a limit of 2.4 meters for its mirror. It had to fit inside the cargo bay. Right. They went up to the Hubble Space Telescope, and they took out one of the instruments, and they replaced it with something called CoStar, which was essentially a pair of glasses for the Hubble to allow it to see now things in focus.
Right.
And in fact, going forward, every camera that was put in the Hubble, I think there's been like 5 missions to the Hubble Space Telescope over its lifetime from the shuttle. Anytime you put a new instrument, a new camera on board, you built the defect of the main mirror into that instrument, so it corrects for it.
That's what you do.
Because the instrument that polished the mirror to the wrong shape is on the ground, so they know exactly the specs of that that ground equipment, so you can compensate for that in any additional instrumentation.
Right.
So that's why I have these nice, beautiful in-focus images of different objects in the sky.
Instead of myopic ones.
Yeah. So anyways, so NASA had to go to the Hubble. In fact, they had to replace gyroscopes, which became a major issue. The Hubble needs to know where it's pointing to take accurate images
Right.
of the sky. And when the gyroscope starts to go, you have to replace them. And so this takes human intervention here. You need to get to the... So we've done... But the Hubble's in its own orbit. So the shuttle had to go up for launch for that sole purpose of getting to that orbit.
Yeah.
It's not like the orbit of the Hubble is such that you can move alongside of the International Space Station, which
And just
maybe
have
would...
them drift out from it.
By hindsight, that would have been better, but the International Space Station wasn't in orbit at the time, and just have it, just have a slow rendezvous, and then you get out and make all the repairs you want. That would be cool. In fact, Hubble should have a repair now to prolong its lifetime.
Yeah.
And Jared Isaacman, so this is an interesting side story here, who's the new NASA administrator, he actually proposed that he would go up and help pay for it, because he's gone up a couple times already. He'd actually go up on a dedicated mission to try to repair the Hubble, like outfit a Dragon capsule. And in fact, his last mission that when he went up, he had an airlock installed in the Dragon capsule that they could take the air out of the capsule itself, and you could stand up and look out into space. So he did that. That was sort of a spacewalk.
Right. I remember.
You remember that?
Yeah, I remember.
Well, that was kind of proving the technology that if you built that kind of airlock to the Dragon capsule, you'd allow you to do EVAs.
Right.
So you could get out, and they put hand railings on different parts of the spacecraft. You go back into the instrument bay, pull out something like gyroscopes or something, and replace them on board the Hubble Space Telescope from the Dragon X capsule.
Right.
Now, that was never approved, that project, and I don't know what's going to happen in the future, if it will or not. We'll have to see. But anyways, that was an idea.
Let's face it, with the way things are going, Hubble's probably about to be deorbited.
Well, I mean, the space station, the International Space Station, is planned to be deorbited around 2030.
Right.
And the present goal is they're going to attach a Dragon capsule to it and then have it slow down so that it re-enters Earth in such a way that it falls in the Pacific Ocean.
Yep.
Oh, one thing you could do if you didn't like that, of course, there's a lot of money. I don't know how much money has been spent on the internet, $100 billion.
Right.
You could try to boost it into a much, much higher orbit.
So that it didn't need the fuel.
Try to use it later or something, but I mean, components wear out, and if you're not on board the spacecraft for long periods of time, and I mean years and years, thing will degrade, and maybe it's not even safe to use. Other people suggest that maybe private companies can take it over, and they can outfit it, make it better, make it more robust if you like to stay up there a lot longer, and use it as a hotel.
Right.
So people who have the money, they can launch, from the Earth, go up, spend a week or something on board the private space station, and like buy it from NASA, buy it from the U.S. government, and do their own thing with it. And so we'll see what happens. But right now, as far as I can tell, it's leaning towards deorbiting in 2030.
Right.
So, but China, yes, has built this idea where they can service the telescope from the space station, which is pretty smart in some sense. It would save a lot of hassle. Now, the details of what the Space Telescope is all about, it's slow to be released.
Oh, of course.
But that's the way it always is, maybe, when that type of government. But there was some mock-ups of the telescope that's been available for a couple of years now, and that's the images that you see here. So these are on displays you can read from the National Museum of China. And notice it looks, if you think of that as a space telescope, number one, it doesn't look like it at first glance. We're so used to seeing the Hubble with his big, long solar panel sticking out on either side.
Solar panels are a lot more efficient, though, nowadays.
That's it. And you can see actually a solar panel there on the side of the telescope, on the side of the body, to help generate the power. And you can see the aperture door. So on the image on the left, the door is on the left of the vehicle that would pop open. So you protect the optics then during launch and then released into the orbit it needs to be in, and then the door will open. And notice that if you do have a problem, let's say something happens to the motor, the actuators on board, that it cannot open the aperture door fully, only partially. Well, if the telescope is on its own, that's it, right? It's done.
It's done, yeah.
But you could have it near the space station, and then you could do an EVA and go out and then pry open, hopefully, the aperture door and So then you can have a light fully come down the middle of the telescope to come to a focus. So you can save it. So it just looks weird. And the image that's on the right, because we're not used to this type, that's all. That's why it looks weird. But the image on the right panel, if you look on the right end of the telescope, you can see a docking port. So you can dock it with the space station and do things, right? To keep it fixedly mounted so it's stable, and then go outside the space station and do your spacewalk and so on. So it's all set up in this way to have direct interaction with the Chinese space station and therefore interaction with the Chinese astronauts that will be on board.
Nice.
So it's nice when you think about it. Now, what does it have in terms of instrumentation? Well, here are some of the figures I grabbed from some of the research papers that were just published a couple weeks ago. And there was a slew of them, so they did sort of a data dump of papers describing all of the things they want to do with the telescope, all the different simulations, what are the optics on board. So finally, we're getting all that detailed information that we are waiting for to see what type of telescope it would be. So I just chose 3 of these sort of figures. One that you see on the upper left is actually showing the optics path, the optical path of the telescope itself. So light comes in, it would hit the primary mirror, labeled M1, gets reflected. So this is the one that's 2 meters in diameter on the right side that you see on that panel, figure 2. We reflect off of that mirror, go to a secondary mirror, then reflects off of that. It hits a tertiary or a third mirror, and then they have another mirror there for steering. So if they're rapidly moving the objects in the field of view, that you can steer it to make sure the light falls on the focal plane, which you see there also labeled. And that's where the detector would be.
That's a lot of components for an optical system.
Yeah, it's not simple. It's not simple, but of course you test it on the ground like crazy. Yeah. Test it in a vacuum chamber and all these kind of things to make sure it's going to work. Now, the camera itself, in terms of the number of CCDs, you can see they're actually in the bottom. Okay, you can see a diagram of the focal plane itself, and it has 30 detectors, so 30 CCDs. And in this case, so it's like a square. You can see them laid out there. And each one has lettering associated with it and also numbers, but the letters themselves associate what filter it's looking at. And the filter part of it is on the top plot above that, so the top right plot. Has wavelength on the bottom, units there is in angstroms, and then we have throughput, or how sensitive is the filter in terms of how much light, what percent of the light does it allow through. So if it's at 1, which none of the filters are at, that would allow 100% of the light that hits the filter gets through. And notice that you have different types of filters. So the one on the far left, sort of the purplish color line, is a near ultraviolet filter. And if you're in space, you don't have to worry about the ozone layer, so you're not encumbered by the Earth's absorbing effect of our atmosphere. So you can observe into the ultraviolet, so that's a good thing to have. The next filter, a little longer than that, is a U-band filter. So we can make observations from the ground in the U-band. They're not that sensitive because a lot of the ultraviolet gets absorbed and scattered by our atmosphere. And obviously you can do a lot better when you're in space. Then you go longer to that, you're in sort of in the optical, so it's a G-band. That's sort of in the bluish sort of visual part. Yeah.
Blue to orange.
Then you're in the R band, so that's more of the red part. Then you're into the I band, so that's like really long wavelength red. And then you're into the Z band, and that's like pegging out into the infrared now. And then finally you're at the Y band, which is way out in the infrared. So take advantage of the fact that you're not going to get absorption by water vapor, for example, and carbon dioxide in our atmosphere, which loves to absorb infrared light. That would not be in existence, of course, if you're in space. You don't have to look through the atmosphere. So you're taking advantage of very short wavelengths, very long wavelengths, and then filling everything else in between.
Yeah.
And the other interesting thing is they have 3 of these really broadband filters labeled GU, GV, and GI. I don't know what G stands for. Giant? Great? Whatever. So the GU filter is very, in terms of its band width, is very large compared to the other more narrow band filters. Mm-hmm. And that just means you can allow a lot more light to come through and see fainter objects in that band. So you can do it for, if you don't want fine sampling of the spectrum of the object, these sort of photometric redshift type of stuff that we can do, then you just want to detect things, and these are the kind of the filters that you would want to use. In fact, a lot of telescopes don't use any filters when you're looking at something extremely faint.
Right.
But you just can't tell anything about it or color which means that you lose information about potentially their composition because of the loss of filters.
Or the processes going on inside them or things like that.
Right, but if you're just solely trying to detect something, you want to capture as much of the light as possible. If it's a really extremely faint object, then maybe having no filter is the way to go.
Right.
That would allow you to get the maximum amount of light and therefore go the faintest in that sense.
That's it.
Yeah, so that's pretty cool. So
pretty cool
that's supposed to be
instrument.
launched in a couple years, at the end. One report I see in the end of 2026. I don't think it's going to be ready for then. I think they revised that now, and it's supposed to be launched sometime in 2027.
Okay.
So that's the ideal here. So we'll
Cool.
see how all that makes it. Now, the next thing I want to show you is actually something fun.
Cool.
It actually shows you the nighttime sky, which is the panel on the right, and where you can see certain sort of famous spacecraft. So starting with the first one is, where is the James Webb Space Telescope? So let's say you're outside at night. Yeah, it's warm around here, so it's in the spring or something, or then you wouldn't be able to see this, but let's make it, you're down south further, put it that way, okay? Or it's not so cold. And people go outside and are with you and they say, oh, I want you to show me some things and like the constellations, stuff in the sky. And it's nice and clear tonight. And then they might ask you, oh, I hear all the news about the James Webb Space Telescope. Could you tell me where that is in the sky? Can you actually point to the location of where we'd expect the James Webb Space Telescope to be? Well, if you watch this podcast, you can do that, at least for
a few days.
For a few days near the end of this month in January. And that's what you see there on the right. So you see a couple constellations. We have Gemini and Orion, which are winter constellations, essentially. Mm-hmm. And you notice there's sort of a yellow curve sort of between the two constellations. And there's dates. There's one January 19th starting on the far right. Then you're heading towards the left, January 25th. And then finally the end of the month, 31st. And that's the location of the James Webb Space Telescope in the sky relative to us. Now, the James Webb is at the L2 position.
So you're not going to see this with your eye, folks.
So it's moving around. It's not like it's stationary relative to us. So it's moving around. And that movement around that point is what you're seeing here, right? In the combination of the motion of the Earth and the motion of the telescope itself. So it's station keeping at the L2 position. So it's not like some people think it's a stable position, like you set the spacecraft there, like you're at the center of a teeter-totter or a seesaw, and it's not going to move. But no, it's moving around. It's
in orbit
dynamical
around
stability.
The center of L2.
Yeah, it's a dynamical type of stability, not stationary. Yeah, so that's where the James Webb. So if you wondered where that telescope is, this is the perfect time of the year to point it out to people.
Yep.
Now, the next one on the list, then, is... Which one is this, Robert?
Europa Clipper.
Europa Clipper. Now, we've had Bonnie Beretti here on our podcast about a year or so ago. She's one of the main scientists that works on the Europa Clipper. This is a mission that was launched not that long ago.
Not terribly long.
Like a year or so ago.
Yeah.
On its way to the Jupiter system to look at the moons, in particular Europa of Jupiter, and to study them. It has radar on board, so you can try to map what's going on the surface. In terms of, one of the big questions, is there a subterranean ocean on the surface of Europa?
That's the big question. Yeah.
And if there is an ocean, could life potentially have formed in that ocean?
Right. And, all these planets are yours except Europa. Do not approach Europa.
Too late.
Oh, whoops. That was a 2001, 2010 reference to the Arthur C. Clarke stories.
Yeah, so the idea is, you can imagine in the future, mankind drilling holes down through the ice shelf and then sending submarines, and they can be, drone submarines.
Right.
That are going everywhere looking for any type of life form. That'd be kind of cool.
That would.
But we don't know if that's the case, 100%. If there is a subterranean ocean, we infer it from density of the moon.
And magnetometer
readings,
measurements. And so forth.
And so we'll have a lot more to say about if we're still doing this podcast when it arrives in the Jovian system in 2030. It's not that long. It's only 4 years. We're on our 4th year.
Absolutely.
We can make it, right, Robert?
I think so.
Stay healthy for me, please.
I'm trying. I'm doing my best.
And so I'll have more to say about what are the details of how you do this type of study. So it's really interesting.
Okay.
Now, this particular object is not going to land on the surface of Europa. It's not going to drill a hole down through the ice sheet. So
It's not even going to go into orbit around Europa.
no, it's not. It's going to maintain the orbit around Jupiter and pass occasionally close to Europa to do its measurements. But it's like another step in all the other steps we've taken so far, with the Galilean mission, with the Voyager 1 and 2, the Pioneer missions all flew by Jupiter, trying to advance our understanding of the
I got to
planet.
admit, I don't know how you get in orbit around Europa. It's so tiny, and you're right there at Jupiter. I don't know how you get to orbit.
I wonder if you could take the motion of all the moons that are around Jupiter, and the main ones, let's say the 4 Galilean satellites, and get a computer, AI,
And simply do a gravity assist from
figure
the
out,
other moons to
exactly,
drop it in.
to figure out some complex type of trajectory that would utilize the gravity of the moons to slow it down to actually be captured by Europa.
You would almost have to.
Or
Because for those that don't know, Ganymede, the largest of Jupiter's moons, is the largest moon in the solar system, and it's actually bigger than Mercury. So not only do you have Jupiter's gravity to contend with, you've got objects like that in the system, in the neighborhood, that you've got to contend with.
The other thing you could do is have ion thrusters, which produce very little thrust, but you could have them run for weeks and months.
Right.
And you could have them a course correction as you continue to make passes by in the Jovian system and maybe get ever closer and closer and closer and closer, refining your orbit till you drop. That's probably the most efficient way of doing it.
But it's going to be tough.
Other,
That's a problem.
The other way is, we've gone into orbit around, Mercury.
We have.
And that's tough to do. We had to do flybys of Earth and Venus and Mercury several times to slow down enough to get captured by Mercury because you're going so fast close to the sun. Or in the future, you have nuclear propulsion. You stick on those engines and burn them for an hour, and you slow down enough to.
Yeah.
That's in the future.
It's a problem to think about right now.
Yeah, for sure. Now, where is this Europa Clipper? First of all, it is not currently in orbit around Jupiter. It's on its way to Jupiter. So it is moving then relative to us in the sky just for the fact that it's journeying to Jupiter.
Yeah.
And if you look and you can see in the southeast, just before dawn, you can see a couple constellations. These are summer constellations like Scorpius. The summer, that's the constellation that you would see if you're in the northern hemisphere in the middle of summer, let's say in July, and you look due south. Right. You will see the heart of that constellation, Antares.
And if you're up where we are, you won't see much of it.
Yeah, a lot of it sticks below. In fact, that's looking towards the center of our Milky Way, in that general area. And you can see the path in a Europa Clipper for those days in January, as we talked about already for the JWST telescope. And so you'll be able to see where a Europa Clipper is. Now, you're not going to be able to see this with your telescope.
No.
It's not going to, even though it reflects light, the amount of light coming off this spacecraft is so feeble that you're not going to be able to see it.
Comparatively, it's a tiny object.
Very tiny. So it's not going to reflect much light at all. But that's okay. You can still point out to people, hey, if you're in that general area, that's where the Europa Clipper is right now.
Yep.
Moving on to the third spacecraft to look at. This is the JUICE mission. This is a European Space Agency mission, also on its way to Jupiter, to study the Jovian system, as we say. And just like Europa Clipper, it's going to go into orbit around Jupiter and study its moons and Jupiter itself. It's actually going to arrive about 1 year after the Europa Clipper mission. So it's supposed to arrival time in 2031. Now, it's interesting. There is a book out there. Michael Brown wrote a book about the Europa Clipper mission. And it details the struggle of scientists, planetary scientists, to come up with an idea for a spacecraft, to get other people excited about it, other planetary scientists, to come together and put together some kind of plan that ultimately you write a proposal to NASA to see if you can get the funding to start to work on it, phase 1 if you like, to get it all, go all through these steps that you need to go through, all the different phases, jump through all the hoops to actually get it fully funded and then launched. And in terms of the Europa Clipper, that was decades in the making.
Right.
And I know others have done this as well. I mean, for example, the New Horizons spacecraft, which flew by Pluto, it gave us our first good view of its surface back in 2015. People who did that spacecraft went through a lot of effort, and it was on the verge of cancellation, and it was modified and revised and all my. It's like if you're a planetary scientist who had, you only, like after you get your PhD, and then let's say you're ready to go to work, even as a postdoc, and you're joining up with one of these ideas.
You usually get one mission.
Yeah, because it can take 20 and 30 years for this stuff to go through. And you got to have a lot of patience.
Mm-hmm.
A lot of patience. That's why you're a doctor, because you have a lot of
patience. Wrong type of doctor.
Well, okay. There's a joke there somewhere. Anyways, but you got to have a lot of patience to be able to stick with it. I mean, how many people would just give up after NASA said no the first time?
Right.
It reminds me as they're like NASA astronauts. I forget the person's name. It was something he was talking about recently, that it took him like 7 or 8 times applying to become a NASA astronaut before they finally accepted him.
Yeah.
And how many people apply once and say, and you get turned down, okay, I'm done, I'll move on to something else, right?
Right.
I mean, he said no, and he applied again and again and again and again and again, and finally, persistence paid off.
Put him on the roster. Shut him up.
Yeah. Get him in space. In there, no one can hear him scream.
Right.
I want to be an astronaut. We can't hear him. He's in a vacuum of space, so we're all fine now. But yeah, just the amount of sort of, I guess, desire and motivation. That's the big thing. How can you stay motivated through all those decades of trying to get your mission to the successfully launched, and then wait for it to get there?
Yeah.
And then all the analysis that happens afterwards. But of course, that's the fun part, right? You get all the data coming in, and it's like
Christmas. The fun starts.
It's like Christmas Day all over again when you're like 7 years old.
Yeah.
And getting lots of stuff, hopefully. Yeah. Anyways, so hats off to these people.
Oh yeah. I was trying to be one of them. So.
To stick with it, right? It's a lot of, and it shouldn't be like that.
No, it really shouldn't. But
right? Why should scientists have to go through that? I mean, I know you have to vet out all the stuff and make it better and better, but you think we come up with a better and a faster way of doing this. You have a great idea, then we have the experts at NASA or some other place to make it happen. Let's work with you to make sure that it goes through, and we'll launch it in 3 years.
Right.
And this was a bit of that motivation that we talked about last week in our last podcast, where we had the private funding, remember, from the ex-CEO of Google and his wife, the Schmitz,
Right.
putting together this group to support, that have funding for 4 different telescopes, one of them being a small space telescope. And the thing is, they were going to, from the time that they had the concept to when it would be on station in space, 3 years.
Right.
Not 10,
I don't think they'll get there, but...
Not 10 years, not 20 years, but 3 years.
Yeah.
So that's the other thing, right? It takes so much time to from the time of conception to get this stuff actually functioning.
And then it's all the money, just basically having it designed over that long a period of time. You're 100% correct. There's got to be a faster way.
You would hope. Now, Robert, for the JUICE mission, you look near Scorpius and notice the constellation right above it. And I want you to pronounce the constellation.
Ophiuchus.
Very nice. Can be a tough one to say.
Yes.
And of course, there are different pronunciations of the constellations. In fact, you can go online and say, how do you pronounce the constellations? All 88 of them that we have. And those pronunciations, sometimes there are more than one way to pronounce them.
Yes.
Because especially the ones that are extracted from way back in ancient
Greece and
Roman mythology and stuff. Do we really know exactly how something is pronounced?
I've watched plenty of videos on how we know what ancient languages sounded like. And the answer is we can make good guess.
We don't know for sure.
We don't know 100%. In fact, I read a good science fiction story that pointed that out, that it was a time travel story, which I generally don't like because of all the inconsistencies involved. But this story pointed that out, that we think we know how Middle English sounds, and we were close. But it took the person that traveled back to then a few days to make all the connections and go, oh, and it was mainly because of the colloquialisms and the accents.
Well, think of the writing. Just go back, look at the writing of the founding fathers of the United States.
Right.
You see the letter F, but that's not an F like it is in our modern language. So the English language, like other languages, all other languages, is not static.
Right.
It's constantly changing. And you have to, go along with those changes, right? Time.
It's like, I had somebody point out, how well can you read Egyptian hieroglyphics? And I was like, I can't. And they're like, that's 7,000 years. So this is why we have trouble with nuclear waste spots. How do you identify this to somebody 7,000 years from now? Because the language will not be anything close.
Well,
to what it is.
that's a good segue into the next slide.
Okay.
And the next slide is, where is the Voyager 1 spacecraft now? And notice it's also in the pre-dawn sky in late January, and it's near that same constellation that you love.
Ophiuchus.
Now, what is so special about Voyager 1? Well, remember, that was one of the two Voyagers that did sort of the grand tour of the solar system that flew by Jupiter and Saturn and really close to Titan in the case of Voyager 1. Voyager 2 didn't go as close to Titan, therefore was able to go to Uranus and Neptune. Mm-hmm. Now, Voyager 1 is the furthest spacecraft of the two away from the sun. So I looked, there's websites you can go, what is the present distance of the Voyager spacecraft from the sun? And you want to say the sun, not the Earth. Because the Earth's moving in its orbit around the sun. So that distance can vary over the course of a year. So really we want to get where the center mass of the solar system is located, and that's near the sun.
Right.
And presently, as of yesterday, the Voyager spacecraft, Voyager 1, is 169.5 astronomical units from the sun. Now, someone will say, what is an astronomical unit? It's the average distance of the Earth to the sun. So Voyager 1 is almost 170 times further away from the sun than the Earth is.
That's kind of crazy.
And it was launched.
I remember when this thing was launched.
1977.
Yep.
It was launched.
I remember being plunked in front of the TV to watch it.
Now, the thing is why it was a segue to this slide is because there is something on board this spacecraft called, what I'm getting at? The gold disc, which is a record. And who uses records nowadays? But it includes a needle to go with it, where we have information on the record about culture on Earth, including songs,
language,
different languages. There is instructions on the disc to how to use it. So getting back to your argument about the hieroglyphics from back in ancient Egyptian times, the ideal is that maybe, and it's a long, long, long shot, even a longer shot than winning the Powerball,
yes,
some advanced life form will find Voyager 1. And they will examine it and see these markings on the surface of this disk and know that they're not natural markings. They are made by some intelligent. In fact, the spacecraft itself would tell you it was made from something. But how do you interpret the markings, which is instructions to play the record?
Right.
And they do it by diagrams, which is what is really the Egyptian hieroglyphics. They are diagrams.
Right.
They are not characters of some alphabet that they will never have a clue about.
And the diagrams are interpretable because there's a lot of lead up to them where we use prime numbers and Fibonacci sequences and then show coordinates of where the star system is. And, it is feasible that somebody, because I'm going to call them somebody, could figure it out. But it's going to take them a lot of work.
It is.
Who says they even have sensory organs like ours? Our eyes may have some completely different sensory system.
Did you ever read that book that's written by the person that wrote the book The Martian?
Andy Weir?
Yeah. Did you read his book about meeting of extraterrestrial life?
I have not. I don't even know which one that is.
The Hail Mary?
It's Hail Mary? Okay.
Yeah. The movie's coming out in March.
Yeah.
And because of that, I got the book over Christmas and read it.
Okay.
And that's exactly the life form that he encountered. They didn't have eyes like us. Okay. And in fact, they communicated through sound, notes, musical notes.
We've done that story before.
So he had to put together a whole way of using computer to figure out if you said something, and he said a note and you're referring to some object, like you have some object, and the life form released some sequence of notes that sequence meant a name for that object, essentially.
Right.
And they couldn't see like us. They didn't have eyes like us also.
Right.
So
it's an awesome thing to think about. How would you communicate with something? Maybe they communicate by pheromones, by smell.
and if you're writing a book and you're an author and you should plug your book or at the end of the podcast. So what's the name of your book?
My book is titled Mortal.exe, and it's about the daughter of Hades and Persephone going to university to study computer science, and mayhem ensues.
And can you get the book from like Amazon and other places?
Absolutely, Amazon.
So look for Robert's name, Robert Moore Jr., and look for anything written by him, and you should be able to find his book.
Yep.
That was just released 1st of January,
1st
right?
of January.
1st of January, so it's out there. But imagine you as an author trying to come up with what would be the first encounter of humans with some alien life,
Right.
intelligent life. What would that look like?
And my statement is, it's going to be stranger than anything I can imagine. I guarantee it.
And what's the common thing that we always show in movies and everything? These grave forms, right?
Right.
With eyeballs and bald heads and, little tiny creatures, essentially, right? 4 feet high or whatever they are.
Those are more likely time travelers than they are.
Well, they
aliens.
almost look like us more than like you haven't imagined enough. You need to work on your imagination a little more.
Absolutely.
Because that's probably closer to what it's going to be like.
Now that I agree with several other people who've spoken on it, they're not going to be these multi-leg things, because so much of your brain power goes to driving limbs. And after a certain point, you're not going to have enough brain power to do anything but motivate your limbs. So, we can actually kind of say these things probably are unlikely, but sensory systems, who knows what's out there?
Robert, do you think we could get Andy Weir on as a podcast guest?
Probably not, but it might be interesting to try.
Yeah, there's no harm in trying, right?
Absolutely.
Okay. So, anyways, thank you for watching. As always, if you're interested in anything we've talked about, one of the ways, if you're personally like to get in more details and learn about astronomy and astrophysics and math, anything about writing, how do I write a novel? I mean, where do I start? And Robert's the person to ask about that since he's done that. You can come to places like the University of North Dakota.
Right.
And we have lots of really interesting programs that we run here on campus as well as online. So you don't have to physically come here in January if you don't want.
Where it's minus 20.
If you're one of these people that rather live in Florida or Hawaii, you can take classes from Hawaii and from Florida
Absolutely.
at UND. So don't be shy. Give us a look on the web and see what we have. Now, our next podcast will be January 27th.
Mm-hmm.
So 1 week from today. And at the end of our podcast, we always do a quote,
Yeah.
or say a poem or an excerpt or something like that. Today's a fairly long one, Robert, and
Okay.
it's related to the moon.
Okay.
And this ties into what we talked about at length today regarding like the Artemis project and so on. And so the excerpt is from a documentary called The Greatest Adventure, which
Okay.
came out in 1979. Narrated by the one and only Orson Welles.
Oh,
I wish I could do his voice.
absolutely.
Reading this.
That would be like Morgan Freeman or James Earl Jones.
Yeah, exactly. So it's like, I mean, how could you top that? Well, you can't. So I'm going to do the best I can. Now, this was a statement, an excerpt, like I said, from the documentary, and it relates to the moon and our feelings about the moon before we landed on the moon in July of 1969. And it's relevant today. So hopefully this is like, get you going at a gut level that, yeah, let's get back to the moon. Let's pick up that exploration of the closest natural satellite, that we have in that sense, right?
I agree.
So here's the excerpt. The moon, goddess of the night. Nothing has so captured the eye and mind of man. On summer days, she haunts our daytime sky. On winter nights, she dominates our dark dreams. Her changing face marks our weeks and months, and she orders the tides of Earth's oceans. She beckons, and all things respond. What makes the grunion run? What brings the starfish out to feed? What alone eclipses the sun? The moon, so enchanting, so mysterious, and so far away that only in his dreams could man touch her barren beauty.
Nice. I can actually hear Wells saying that.
Anyways,
I may have. That may be why.
thank you very much for
Thank you,
watching our
folks.
podcast. Please remember to give us a thumbs up, subscribe if you haven't subscribed, and we'll see you next time.
Later on, folks.